Hello all, thanks for attending my presentation. My name is Minxiang Gong. I'm a graduate student from Georgia Institute of Technology. I joined this Asian task in fall 2019. This task is focusing on designs of topologies and controls for a package-integrated high-voltage converter. Today, I will introduce our progress on a 48-to-1V single-stage GaN-based package-integrated power converter. This is the outline. I will first introduce the motivation to 48V power conversion in data centers. Then I will present current work on a single-stage synchronous buck converter. Then I will talk about hybrid topologies, which show promising results recently. Finally, I will give conclusions. First is the motivation. This figure shows the current and future power distributions in data centers. First, they both have an AC to DC converter serves as the front end to generate a 48 DC power bus. The difference appears on the server rack. In the current system, it uses two-stage solution. It consists of a 48 to 12V DC converter and a 12 to 1V point-of-load converter. It is limited by the two-stage cascaded conversion and high loss on the 12 DC power bus. In the future system, there is no 12V intermediate power bus. The 48V input is directly connected to the processor package. By doing this, it reduces losses on the motherboard and the power bus. It also reduces system volume significantly. Therefore, a 48-to-1V converter is highly desirable. This slide shows the efficiency comparison between conventional two-stage conversion and single-stage conversion. From the figure on the right, due to the multiplication effect of cascaded conversion, the single-stage solution shows better overall efficiency around 90%. Moreover, since converter's efficiency is low at light load conditions, two-stage solution has more light load degradation, while a single-stage shows wide dynamic range. This slide shows the size comparison. For a half-bridge converter, the required inductor value for certain inductor current ripple at target switching frequency is calculated by this equation. The corresponding figure is shown on the left. The inductor for first stage depends on its output voltage, while the second stage shows small variation. The conventional 12V intermediate voltage requires 9 microhenry for first stage. However, if we choose single-stage conversion, the required inductor value is only 1 microhenry, a significant reduction. Therefore, a single-stage solution is desired based on efficiency and system volume. Now I will talk about current work. This slide shows our current work on a 48-to-1V two-phase synchronous buck converter. It features package-integrated GaN power FETs and all-digital silicon controller. In the controller chip, a 4-bit time domain ADC converts voltage difference between output voltage and reference voltage to a digital word. The PID controller provides stability compensation. The pulse width modulator generates proper driver signals. A programmable dead-time controller fine-tunes the delay between high-side and low-side drive signals. At last, the driver signals are delivered to the gate of GaN FETs via level shifters. A bootstrap capacitor is used to provide a high voltage supply for drivers of high-side switch. The chip is fabricated in 180nm high-voltage BCD process and occupies an area of 5 mm² per phase. The controller chip, GaN FETs, and the bootstrap capacitor are heterogeneously integrated on an organic FR4 package substrate using standard techniques. The inductor and the output capacitor are on the PCB board. This slide shows circuit diagram of time-based ADC. At first stage, the voltage difference between output and reference is converted to 2 clock signals via current stubble delay lines. The phase difference between clock signals is converted to a 16-bit thermometer code. Finally, the thermometer code is converted to 4-bit digital word by an encoder. This architecture achieves high resolution around 1 buffer delay. The dead time related loss is essential at high frequency. Simulated loss breakdown is shown here. Now optimized dead time takes around 12% total losses. Since the dead time largely depends on load current and varies die to die, we propose a programmable dead time controller for accurate tuning. An 8-bit word is sent to the mux that choose proper delay between two drive signals. This slide shows measurement results. This figure shows the power and the duty ratio for certain output voltage. We achieve 12-watt max power delivery at 48-volt input. 2.4% minimum duty ratio is achieved, which means high side on time is only 5 nanoseconds at 5 MHz frequency. This is fulfilled by package integration, which reduces parasitic capacitance. The second figure shows load regulation. 31 microsecond recovery time is achieved with 120 millivolt voltage droop. This figure shows load regulation error. Based on the accurate voltage sensing, a 2% regulation error is achieved. This figure shows measured efficiency at 48 volt and 24 volt input. We achieve over 76% efficiency at 48 to 1 volt conversion and 86% efficiency at 24 to 1 volt conversion, both at 1 MHz. Efficiency at 5 MHz is lower because of switching losses. This figure shows figure of merit for high voltage converters. It consists of frequency, input voltage, and conversion ratio. Each of them is related to design parameters. Higher form reveals challenges of efficiency and implementation. This figure shows the form and the efficiency plot of high voltage converters. First, we achieve 13% improvement of form over state of the art. Compared to the work published on JSSC 2017, we show 14% improvement on efficiency, while we have 3 times higher conversion ratio. GaN power FETs, which are circles, also shows superiorities over silicon devices. This table summarizes our work. We demonstrate the first package-integrated single-state 48 to 1 volt synchronous buck converter. We achieve high conversion ratio while maintaining competitive efficiency numbers. We also support high current and use small value of passive components for dense integration. Now I will talk about hybrid topologies. This figure shows the limitations of synchronous buck converter. Although we keep the same frequency, output voltage, and current, the simulated total losses increased over 3 times as the input voltage increases. On the other hand, the high side on time decreases to several nanoseconds. Such short on time not only prevents us to further shrink the system volume, but also increases AC loss on the inductor. These two limitations of a synchronous buck converter reveal major challenges in high voltage converter designs. Since they both scale with the switching voltage, techniques to reduce switching voltage become the key point in high voltage converters. Let's go back to the inductor size figure. Instead of using inductive in the first stage, we can use capacitive stage with small area overhead. Thus, the topology has both switching inductor and switching capacitor features. The 3-level buck converter is a good example of hybrid topologies. The inductor is always charged by a flying capacitor instead of input voltage. Thus, the switching voltage on the inductor is reduced, as well as voltage stress on switches. Therefore, it reduces switching losses and extends the duty ratio. Another example of hybrid converter is a series capacitor buck converter. Compared to 3-level buck converter, it has 2-phase interleaved operation that reduces conduction loss and can support higher output current. The 2-phase operation can be embedded to capacitor charging and discharging state. Therefore, it is always desired for high current applications. The simulated efficiency is shown on the right. It shows good improvement over a synchronous buck converter, especially at 1 ampere to 2 ampere, where switching loss dominates. Obviously, 2 times voltage reduction is not enough for 48 to 1 volt conversion. Higher level SC structure is required. Among various SC structures, TECHCON converter shows its advantages of high switch utilization and intrinsic phase duality. With small number of switches, it brings down voltage 4 times. From efficiency plot, it shows good improvement even at heavy load where conduction loss dominates. However, because of high gate driver loss, efficiency at light load decreases a lot, and it requires split phase control to achieve complete self-charging between flying capacitors. To address the above issue, 2 more inductors are added to provide self-charging between flying capacitors. Now, each capacitor is connected to an inductor, so all capacitors are charged by inductors. Since there is no capacitors connected directly, thus, it achieves self-charging without split-phase control or capacitor sizing strategy. Control complexity is greatly reduced. Now I introduce another kind of hybrid topology. From above discussion, SC converters can bring down voltage efficiently, while buck converter is good at regulating the output. The buck converter can serve as a current load between capacitors to achieve self-charging, as shown in the figure. Thus, both switched capacitor stage and buck stage are working in the desired condition. The buck stage is operating at a much higher frequency, so the intermediate voltage Vm is not restricted to small voltage ripple. The energy stored on capacitors can be efficiently used. This figure shows another type of merged 2-stage topology. A series capacitor buck converter is used as the second stage, so it achieves 2-phase operation and has multiplication effect of voltage bring down, 4 times switching voltage reduction with 2 capacitors. Let's go back to our form charts. We add hybrid topologies and our simulation results of the chart. We can see that the efficiency of buck topology, which are blue points, is reduced dramatically as form increases. This blue region shows our estimated buck limitation. Because of the on-time limitation, the highest frequency of a 48 to 1 volt synchronized buck converter is around 5 MHz, and the peak efficiency is also restricted to below 80%. The green region shows current walks on hybrid topologies. Current walks are in low frequency range, so their forms are low. However, with our simulation results, we estimate that hybrid topologies can achieve near 90% peak efficiency as form increases. It shows great superiority over buck topologies. Then I will give conclusions. We present the first package-integrated single-stage 48 to 1 volt synchronized buck converter with digital controller IC, which achieves 13% improvement over state-of-the-art. Hybrid topology show promising results, especially for high-voltage conversion. High-frequency operation, dynamic behavior, and integration of hybrid topologies need intense research. These are publications. At last, I want to thank for Dr. Zhang's support to our work. Thanks for your listening.